Okay, hi everybody. Welcome to the last talk of today. So we're going to have Noam Lifshitz, and he'll tell us about the Junta method and applications to extremal combinatorics.
So as Stephen talked about Friedrich's Junta theorem, and it tells us that if we have a function with a small total influence, then it's close to a Junta. Informally, and close, you can think of the probability when you choose X randomly. Close mean, and also probably it's best to recall what a Junta is. So this is also a bad marker. The function is J Junta if it depends on J variables. So we have, for example, we have the function fx equal to xi, which depends on one variable, and we have fx, which is indicator that x1 plus x2 plus x3 is greater than 0. Majority function of 3 variables, and this function is a 3 Junta. So this is one theorem. So, and Friedrich's Junta theorem is one theorem about approximation by Juntas, and these approximation by Junta theorems, they play a central role in analysis of Boolean functions. So another example of a Junta theorem is the Kindler-Safra theorem. And it says that if the sum over S at least D of F at S squared is smaller than epsilon, then F is close to a Junta. This is for Boolean functions. So if you have a Boolean function that has all its mass on its low degrees, then it's close to a Junta. So if a Boolean function is close to a low degree function, then it must be close to a Junta. And what we're going to talk about today is the appearance of Juntas and degrees in other settings, and in particular in extremal combinatorics. Okay, so let's talk about other settings. what are other settings that we care about? One is n choose k. So the family of all subsets of M that have size k. And then we can ask what are the juntas in this setting. We can talk about functions 0, 1. And these correspond to families of sets. So they are in one-to-one correspondence. And we can, if we want to find the analog of the decretor function, we can take the family of all sets that contain I. This function corresponds to the decretor function. And if you want to take the family that corresponds to this function, you can take F to be the families of all sets in n choose k, intersection with the set 1, 2, 3. This is a 3 junta for families of sets. And in general, the definition is going to be that F is a J junta. There exists a set J of size J. So the question whether a set belongs to F depends only on the intersection of A with J. So here we add the set of one coordinate, the singleton of I. If we wanted to know whether a set belongs to F, we just needed to check whether I belongs to A or not. Here it's the same thing with 3 elements. And that's the notion of a J junta. That's for set systems, for families of sets. What about the symmetric group? So here, if we have a function f from the symmetric group to the real numbers, then f is a J junta if there exists a set J of size J, such that f of sigma is determined by sigma of I or I in J. So, for example, we can take the indicator of all permutations that send I to J. This is a dictator. This depends only on the value of sigma on one coordinate. And you can also find something that depends on 3 coordinates. I don't know, the indicator that sigma of 1 is 1, and sigma of 2 is 2, and sigma 3 is 3. This is 3 junta. And it turns out that this notion that's motivated by analysis of Boolean functions, it was actually studied by representation theorists, because this notion of a junta, it actually can be described in terms of subgroups of Sn. So if we have a group action of Sn on the space on L2 of Sn, so this is the space of really valued function on Sn, and we can let sigma of tau be f of sigma inverse of tau. So that's group action. And then f depends on a set J of coordinates if and only if we take the subgroup so we can take the subgroup of all elements that such that send J to itself. If and only if every element in this subgroup sends F to itself. Say that F, yeah?
Don't you want in the junta to be dependent on the sigma inverse also?
Yeah, so there are two notions of juntas. You can define some notion. Yeah, so for this notion of juntas, you can also take the indicator that sigma of 1 is in a set I. This is also a one junta. That's a good point. You can define a left junta and the right junta, and they both make sense. Yeah. We also talk about the indicator that sigma inverse of 1 is in a set I, and then according to our notion, it's not going to be a junta, but it's a junta with respect to the other action from the other side. You have this subgroup of all elements that fix the set J, and F depends on the set J, or if and only if for each permutation in this subgroup, when we basically change the values outside of J, we don't change the value of the function. This is what it means, that when we change the values of the input outside of J, it doesn't change the value of the function. Are there any questions about this? Okay, so that's and once we have this notion of a junta, we can already talk about degree decomposition. So we can say degree from Sn. Wow. The minimal D, which F, the linear combination of D juntas. And so this is a notion for a function, and also define a corresponding notion for representations, but maybe I just stated briefly that you can talk, you can define the level of representation to be the minimal D for which it contains a uj invariant vector for j of size d. So it's the minimal D for which it contains a D junta, but not let's not talk about it too much. But it turns out to be a very important concept in representation theory. So that's what happens in Sn. Let's talk about GLN Q. So there we have the dictators.
Now, you want to remind us what is
GLN, so GLN of FQ, yeah. It's matrices, invertible matrices over a finite field. Yeah. Then we can talk about dictators. These are the functions of the form FA is the indicator that A of V is equal to U. And you have this notion of junta. What does it mean to be a junta? So F is a J junta. There exists some subspace of FQ to the N of dimension J, such that the value of F on a matrix depends only on the restriction of A to this subspace. And then again, we can define a function to be of degree D if it's a linear combination of D juntas. In the Boolean cube, you can see that the characters of degree D, they're all D juntas. They all depend only on D coordinates. Okay, it turns out there is a result from 2019. That use this notion of juntas to, or they didn't call it juntas, but they used they use this notion of juntas to get a breakthrough result in the character theory of finite simple groups. And let's state roughly the result. So we have a class function on a group.
Remind us what's the class function?
Yeah, that's what I'm doing. Okay. So it's a function that's constant on each conjugacy class. These are, and so these are like these nice functions so that that is it's much easier to do Fourier analysis on these class functions that are invariant under conjugation. And all sigma in G, yeah. And G, yeah. So it's a function that's constant on each conjugacy class, yeah. Invariant under conjugation. And okay, these functions are equipped with an orthonormal basis. Characters. These things are called characters, but they are no longer homomorphisms from the group to the complex numbers. They are homomorphisms from the group to matrices, and there are traces of homomorphism from groups to matrices. Okay, so they have this orthonormal basis, and basically you can define the. So these are functions on G. You can. So we have this notion of degree that's defined in terms of what is the minimal D, such that they are a linear combination of D juntas. We have this notion of degree for a character. What the degree of a character is. And okay, yeah. So we said what's the degree for every function on the group. So we said that we have the notion of a J junta, and then a function is of degree J if it's a linear combination of J juntas. And actually, degree is a very bad name because usually for characters, their degree is their value at 1, their dimension. But so it's so maybe.
Are you still in like GLN?
So yeah, GLNFQ or SN for both of them it works. Yeah. So we know what's the degree of chi. This is just the minimal D for which it's a linear combination of D juntas. And unlike the Boolean cube, where it's quite easy to determine the values of the characters on elements, in other groups it's much harder to know their values and even to estimate these. And what they did, they managed to compute. Yeah, so they upper bounded the Q norms of the characters for even Q, and then upper bounded it's just rough, but the upper bounded chi of G whenever set A of all elements in the conjugacy class is large. It's very similar to the ideas that we talked about in the last talk. We have some set. We want to upper bound the value of the character on this set. We can upper bound its Q norm and apply tail bounds to get that the value is small. So chi of G is the inner product between the set and the character. you have to normalize by the density, but you have this thing, and upper bound on the Q norms of the characters, they correspond to upper bound on these values, and these have numerous applications in group theory. And what I'm going to talk today is about extremal combinatorics and the problems that they motivate, where we want to prove upper bounds on the Q norms of arbitrary functions of the greedy that are not necessarily the characters. We want to get an arbitrary function of the greedy and for a general group, and to get something like the level D inequality to show that all the mass of functions on the group is concentrated on the high degrees. So basically, the Boolean cube is a very special case, a special case of something much more general that you can study. Yeah, so you can think about the conjugacy class of a certain diagonal matrix with no high multiplicity of, like the small conjugacy classes are the ones when you have one eigenvalue with a huge multiplicity. But the other ones are pretty small, are pretty large, and then this bound, you get a bound that says that the value of the character has to be really small. Yeah. And basically, you have this set, the conjugacy class, and what the theorem basically says that if you look at the indicator of the conjugacy class, all of its mass is on the high degree. This is like roughly what the theorem says. And these values, chi of g, can be thought of as the Fourier coefficient of the conjugacy class. So what they do is basically upper bound these values and get the conjugacy classes satisfy certain pseudo-randomness properties that are important for expansion and other problems in group theory. It's the same orthonormal basis. It's the, so these are called the irreducible characters, and yeah.
And the sky go from G to
And carry G. So
we require that A is large, the conjugacy class is large. But in the last section, we saw that it's unified small and
it's with
very small.
yeah. So I mean, okay. Yeah. So if it's good that last time we said that this property is a property of small sets, and now I'm saying that it's about large sets.
Yeah.
But all the conjugacy classes are somewhat small. When they're very, very small, it's like one element, I don't know, like the identity, you won't be able to say anything. But they have to be somewhat large in order to be able to say something. But all of them are somewhat small.
Quick question. So the chi, you said are the traces of the irreducible representations?
Yeah.
Okay.
Okay, so let's talk about extremal combinatorics. And so we have the following problem. So we have a function, a family of sets. The question is how large and FB. For A, B, and F, the intersection with of A and B is non-empty. One example of such a family, we can take the family of all sets such that I is in A. If we take its size, this is going to be n-1 choose k-1. And the Erdős-Corrado theorem says that this is the largest intersecting family. Yeah. Okay, so what is the motivation of studying problems in, or at least for people in theoretical computer science to study these extremal problems in extremal combinatorics? So there are a few reasons why I think you should care about them. One thing is that they inspire the development of powerful machinery. The development of the hypercontractivity for global functions was partially inspired by problems in extremal combinatorics for the families of sets. Also leads to connection between representation theory and the theory of Boolean functions. There is this paper by Ellis, Friedgut, and Pilpel. And they basically identify that this notion of level that appears, or degree that appears in the symmetric group, is the same notion of is the same as the notion of Juntas, degree by a linear combination of Juntas. And it also has specific applications in theoretical computer science. So there is this result by Dinur and Safra about the hardness of approximation for vertex cover. So what I'm planning to do now is to give a version of the Erdős-Corrado theorem for the p-biased cube, and then to give a proof for it using the noise operator. Let's do that. So we called it for graphs. We have two models of random graphs. We have G and M. We can choose a random graph with n vertices and m edges. And we also have G and P. And where we choose every edge in the graph to be there independently with probability P. When P when M is roughly P times n choose 2, these models behave the same. Roughly you can do the same thing for the families of sets and talk about the p-biased cube. So now we're going to let the cube be with 0 and 1. And we'll talk about this p-biased distribution. So mu p is the Bernoulli measure where each xi is 1 independently with probability p. And then you can say that a function of the Boolean cube intersecting if whenever we have two elements in the cube whose value that f takes the value 1 on them, there exists a common coordinate for which they are both 1. And then the p-biased Erdős-Corrado theorem says that if f is intersecting, then the expectation of f according to the p-biased measure must be. And that's the p-biased analog of the Erdős-Corrado theorem. So are there any questions? Yeah. So this version implies the p-biased one. In the p-biased case, you can get a rough version, an asymptotic version, maybe the other one, but it's not immediate. But it's like a cleaner version. So you can prove, I mean, GNM and GNP, they behave roughly the same, but GNP is much more nice to work with because of the independence. So you have something similar for extremal combinatorics when you can talk about p-biased problems and you get the same ideas, but the analysis is nicer. We'll give a proof of that essentially due to Fleetwood. And we're going to start by defining the noise operator in the p-biased cube. So let's X be in the Boolean cube. We let n epsilon X be given. By setting yi to be xi, with probability epsilon, and otherwise choose yi uniformly and independently according to mu p. And not uniformly, but p-biasedly. Yeah. We again have this picture of this Boolean cube, but with the p-biased setting. And for every x, we have this small neighborhood of x. Now, the p-biased cube doesn't have the same Fourier basis as the uniform cube, but we actually have to come up with a new basis because the old basis is no longer orthonormal.
So I think of P as an analog of K in the original version.
Yeah, so P is like K over N.
I see.
Because if you choose a set randomly according to mu P, the number of elements in it is going to be very close to P times N. It's very concentrated around its mean. So these problems are roughly the same. Okay, so that's the noise operator, and the Fourier basis for the cube is going to be again a basis of eigenfunctions for the noise operator. So let's construct this basis. So this basis is going to have the constant function. This is very important for applications that the constant functions is a part of the basis. And other than that, we want to complete it to an orthonormal basis. So basically we can take the dictator xi, make its expectation 0, and then normalize. So it will have norm 1. That's a basis for 0, 1. This is called chi-i. Then we let chi-s be the product over I and s of chi. If you can check that when p is 1/2, we get the same basis as earlier. And now it turns out that the same proof from before works. And if we define the operator t epsilon of f of x to be the expectation of y in this small neighborhood of f of y, we get that T epsilon of F is going to be the sum over S of epsilon to the S times F at S chi S when F is the sum of F at S chi S. So this is, these chi S are an orthonormal basis, and we can let this be the p bias Fourier expansion of F. And this T epsilon, it has the same properties of killing the high degrees. So how is it related to the original problem? It turns out that this notion, you can actually extend it to the case where epsilon is negative. So how does that work? We can look at the probability. We can choose x according to mu p, and let y be a noisy version of x. And then we can compute the probability that xi, yi is some vector ab. And then it's going to be equal to, when AB is 1, 1, it's going to be epsilon p plus 1 minus epsilon p squared. So we first need xi to be 1, and then yi, either we remembered xi with probability epsilon, or we forget it, and then we have to be lucky and choose it again with probability p. And we have this probability of 0, 0. This is going to be epsilon 1 minus p plus 1 minus epsilon 1 minus p squared. And you have the case where A, B is either 0, 1 or 1, 0. And then it's going to be, let's look at 1, 0. So it's going to be P. And then we have to forget it. And after we forget it, we have to be lucky. So it's going to be P plus 1 minus epsilon P times 1 minus P. And now you can realize that this notion actually makes sense also for negative epsilon. And, okay. It makes sense for epsilon, which is at least minus p divided by 1 minus p, because all of these probabilities are still going to be non-negative, provided that epsilon is at least that number. And when epsilon is equal to minus p divided by 1 minus p, we have that the probability of 1, 1 is 0.
For the third case, why is it not just 1 minus epsilon times p times 1?
Yeah, I think so. Not P plus, just 1 minus epsilon P, 1 minus.
It's one. So 1 minus epsilon 3 epsilon 3. Okay, and okay, so now what can we say about this expectation? Now we choose epsilon to be minus p divided by 1 minus p. What can we say about this expectation when x p? F of x, f of y, when f is intersecting. What is this thing when f is intersecting? This is what I ask. With 4 possibilities. The probability of 1, 1 is 0. This is the key thing when yeah, exactly. Yeah, so when we choose y according to n epsilon of x, we get that x and y don't have a common coordinate that's 1. So by definition, we get that the expectation of x, f of y is 0. And now what you can do is to say that 0, so this is the proof. Biased. So 0 is the inner product between the epsilon of f and f. The sum of epsilon to the s times f at s squared. This we can write as f at of the empty set squared plus the sum over the non-empty sets now we can lower bound each epsilon to the s by minus p over 1 minus p. And now we can write it as f out of the empty set squared times e to the 1 minus p plus the sum over all s of 1 plus p times 1 minus p, and here we have the sum over all s. And what can we say about each part? So the full coefficient of the empty set, this is the inner product with the constant function. So this is 1 over 1 minus p times the expectation of f squared. And this part here how can we, what's the relation between this part and the expectation of f? Or says that you have 4 minutes to give me the answer. So it's 1 when the function takes values -1 and 1, but here the function takes values 0 and 1. Yeah. So now, yeah. So here f is the indicator. Yeah, it's the indicator of some set. So this is minus p divided by 1 minus p times the 2 norm of f squared. So this is equal to 1 over 1 minus p times the expectation of f squared minus p over 1 minus p times the expectation of f. And when rearranging, you get the expectation of f. If we had the level D inequality, we could have said that all of the mass of f is on the high degrees, and then we'd get something much better than this p here. Think like of p as being small. If the level D inequality were true, then we would get e to the -1 over p. So something exponentially better than the Erdős-Corrado theorem. But it turns out that the level D inequality is not true in the p-bias setting. And instead, we have this pool of hypercontractivity for global functions, and that's what Dor will talk about, that says that in some cases, you can recover this level D inequality. There are these functions called global functions. And these, in some sense, are the interesting functions that are the non-dictator-like functions. And for these, you can get the level D inequality and get an exponential improvement of the Erdős-Corrado theorem. Okay, so I think let's stop here.
Any questions?
So we defined the noisy like neighborhood by setting y to be xi with probability epsilon, but then he took epsilon to be negative. So I was wondering if there's like a nice interpretation of the sampling of y when epsilon is negative.
Yeah, so basically there is a unique way to couple. So if epsilon is at least minus p over 1 minus p and at most 1, there is a unique way to couple the p-bias distribution with itself in a way that you get that the correlation between x and yi is epsilon. And that's
is it just like sampling? So for I guess for the case when epsilon is exactly equal to negative p over 1 minus p, are you sampling y from the bias distribution and then setting all the yi to be 0 whenever xi is equal to 1?
Exactly, and then you have to find the right probability when xi is 1, you have to set yi to be 0. When xi is 0, you have to figure out the right probability in order to make the distribution of y p-biased. It's not going to be p because then it's going to be p1 over minus p. Yeah.
Thank you.
All questions?
Know about these operators, it's at like negative values are like I don't know. The time is like imaginary, or like I'm thinking of the semi group. It's like there's a like it's like you're moving to the imaginary line, or so like these T operators are like e to the LT minus LT.
Right.
So now when you're negative, somehow you're even imaginary line.
Yes, so,
Yeah.
You just have to take a negative value and everything works. Yeah, you do it formally, really.
No, I mean I'm trying to make sense of okay.
No, it doesn't make sense.
Properties.
You're setting. It makes sense when you just plug in the value.
It doesn't have interpretation in terms of random walks.
Okay, if there are no more questions, let's thank Noam again. So see you.